All right, we were just talking about this process of finding an antiderivative, so let's kind of formally define what all of that is all about. So we're starting with a differential equation. And differential equation is probably something that you've heard before, and it's definitely something you've already seen before. So differential equation in x's and y's is just an equation that has x's, y's, and derivatives of y's within that equation. Every single time we've taken a derivative, we have just made a differential equation, right? So here's an example, y prime is equal to x plus 3. That's a differential equation, has x's, it has a derivative of y in it. And so the process of working this thing backwards to find y, that's your main goal whenever you have a differential equation. The process of working that thing backwards is called antidifferentiation or sometimes integration. Specifically, it's indefinite integration because of that whole plus c that we talked about before. Okay, so if I wanted to work this backwards, it's called integration or antidifferentiation, or if I take that function, I take its derivative, I can go back. Kind of is this cycle going backwards and forwards between integration and differentiation. Okay, so then here is a formal definition of antiderivative. A function capital F is an antiderivative of f on an interval I if the derivative of capital F of x is equal to f of x for all x in that interval I. So first of all, we use this capital F to denote an antiderivative. I have my function f of x, which is it's really a differential equation. I want to work backwards to find its antiderivative. I'm going to capitalize that function. That's usually what we do. All right, so we're saying that if I have this capital letter f, if I take its derivative and I get this original function f, that must have been an antiderivative. And remember that this thing that's this interval I, that could be whatever interval that that function is defined on. It could be from negative infinity to infinity. It could be from, let's say, positive 1 to positive, I don't know, 13 or whatever, either including those endpoints or not including those endpoints, whatever. All right, so an example, the same one that we were working with before, f of x is equal to x plus 3. If I wanted to find an antiderivative, it would be something like, here's this first one, capital F, that's the antiderivative, the way we denote it, 1/2 x squared plus 3x minus 1. That's just one possible antiderivative. I know it's an antiderivative because if I were able to take the derivative of this, I would get this x plus 3 business. Okay, so here's x plus 3 graphed over here as a line, and then the antiderivative we just talked about, the whole minus 1 on that parabola. Okay, but that's not it. I could have one that has plus 0 at the end. Graph it, still a parabola. Or maybe I have plus 1 at the end. Or maybe I have plus 2 at the end of it. And so again, you can see that if we just change this last number over here at the end, that it's just moving that parabola up and down. It's just a vertical translation in this particular case. Okay, so if I wanted to generalize every single one of these, instead of having to write down all of these with different constants here, we're just going to summarize them all with this constant of integration called plus c. So if f is an antiderivative of f on an interval I, then the most general antiderivative of f on that interval I is capital F of x plus c, where c is an arbitrary constant, and again we call that constant the constant of integration. It's so important on the AP exam whenever you're solving these differential equations on a FRQ. If you forget your plus c, not only do you lose that point for forgetting the plus c, but you can't get any more points after that. Okay, so usually one of the goals is to figure out what that plus c is, and you can't do that without some other piece of information. You can't do it just straight from the function that they give you, this differential equation that's right here, right? So as we saw, here is a particular antiderivative, and there's an infinite number of them. If I wanted to represent every single one of them, instead of putting this minus 1 at the end, I'm going to put this plus c, okay? And so this represents the whole entire family of antiderivatives. Again, there are an infinite number of them. If we change this constant out here at the end, it's just going to do a vertical translation of every single one of these little functions. It is the general antiderivative of this function f that we started with. And we can also say that it is the general solution to the differential equation f prime of x is equal to x plus 3. In order to figure out what that c is, though, you need another piece of information, an initial condition. In other words, you would need a point that is on this original graph in order to figure out what that c is. And that's something that we'll do definitely in this lesson. Let's take a look at another couple of examples here. Oh, yes, one last thing. It's called the constant integration. If you haven't written something down up to this point, make sure you do. Now then, let's take a look at another couple of examples. Kind of a spectrum of examples right here. All right, so every single one of these things this is an antiderivative of the function f of x is equal to x squared. So if I were to take the derivative of this function, this 3 would cancel out with this 1/3 and just give me x squared, right? So if I take the derivative of this function, I get f of x is equal to x squared. So therefore, 1/3 x squared plus c is the general antiderivative of f of x equals x squared. And this plus c, whenever we change it, we just get these vertical translations of this cubic equation.